Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by David Stillman, who's come across to us from Square in Colorado, the Southwest Research Institute. David did his bachelor's in science at the Colorado School of Mines and his PhD at the same institution. His PhD was on the frequency and temperature dependence of electromagnetic properties of Mars analog materials. He's a near-surface geophysicist with an expertise in electromagnetic methods, and he's currently running the Planetary Electrical Properties and Geochemistry Lab at the Southwest Research Institute. His career is focused on electromagnetic detection of water in planetary surfaces, particularly in the Martian subsurface. And he has published on the use of radar measurements to investigate subsurface of planetary bodies, and also on the role of acids in electrical conductivity of ices in the solar system. Today, however, he's going to talk to us on his recent project of imaging and thermal constraints and a model for the recurring Slope Lineae on Mars. So please join me in welcoming David.
Thank you. Thanks for coming. Thanks for inviting me, and thanks for watching online. And so today, I'm hoping to convince you that these recurring Slope Lineae features that we see on Mars are indeed caused by shallow subsurface water that's flowing right now on Mars today. So I did not do this all by myself. Robert Grimm and Keith Harrison, both at SWERI, helped out a lot, and then also Tim Michaels, who's a SETI Institute employee. So the outline of this paper, or this talk, is first I'm going to describe what an RSL is, and some background stuff on Mars. Then we'll go into the motivation for doing this work. Then we're going to pull out 3 RSL regions, look at what their duration is, their seasonality, and their temperature. We'll look at the formation and recharge mechanisms of each one of these regions. And then we'll compare and contrast RSL regions. And then lastly, we'll do some conclusions and implications. So we're talking about Mars, so I'm going to keep everything kind of in the Martian domain here. So a Mars year is 668 sols. 1 sol is a Martian day. It's a little bit longer than an Earth day. Mars year 1 actually started on April 11th, 1955. So that's a Martian year starts at LCS 0, which is equinox. Then we go into southern summer, which occurs here at the northern solstice. And then we go back to equinox, then we go to the southern solstice again, where it's southern summer. And then Mars's orbit is quite a bit different than Earth's. It's more elliptical. So the perihelion and aphelion distances, which are shown here and here, are quite a bit different. So this actually makes the southern summer a lot warmer. It's about 20 degrees warmer. And we'll see that has some big impact, some big effects on the RSL. So today actually is Mars year 32, LCS 210. So right about here we're coming into the summer and coming into perihelion. So it's starting to warm up in the south. Almost every image I'm going to show was taken by the HiRISE instrument. This instrument's on board Mars Reconnaissance Orbiter, or MRO. It arrived at Mars in 2006. We call this the spy camera on Mars. It's got a 25 centimeter per pixel resolution. It's a pretty amazing camera. And RSLs are really pretty new. They were just discovered in 2011. So this is Tivit Crater. This is in the south mid-latitudes. The diameter of this crater is 3.25 kilometers, just to give you some scale. And we've got recurring Slope Lineae coming in this red circle area. So this is outcropping bedrock here. We've also got outcropping bedrock other places, but we don't see RSL. They only happen in this area. It's another kind of question as to what's going on there. So RSL, recurring Slope Lineae, they're thin, dark albedo features. Where'd the mouse go? So they're these guys right in here. They occur seasonally when the temperatures are warm. So what I'm going to show right now is watch them lengthen. So here we're at LCS 305. I'm going to forward at about 15 sols here, and we're going to see these increase. So you can see how so this is pretty much the cadence of the images that are taken at best, as within 15 days, and you can see how they're lengthening here. This is the first characteristic of an RSL site, is that they must show incrementally lengthen. The second characteristic is they must fade away. So you can see your RSL, just look at your favorite RSL here, and then bam, it's gone. It's faded away, and then they recur year after year. So before we were in Mars year 30, now we're in Mars year 31, and they're starting to come back here. You can see this RSL right here. So these are the three characteristics. More general observations, they typically emanate from patches of boulders or bedrock. They start very narrow, really all the way down to the resolution of high rise, like 25 centimeters. Just these little things flowing. They mix with other ones, forming tributaries. It's kind of happening over here. You'll see better images of that later. And then they just follow existing drainage patterns. They end in fans. This is from another image, more equatorial. These are big fans coming out. There's bedrock down to the south that's just spread out on these fans. And no material ever appears to be transported. Trust me, I've looked. You look at these areas and you're thinking you're seeing ice just melting away, but nothing is ever moving. Every now and then you see a boulder falling down a steep slope or something like that, but it's pretty amazing. There's also no obvious spectral signature of water or salt. So we only have spectra down to about 18 meters per pixel, but you can see here's the scale bar of 25. So 18 meters per pixel pretty much gets you that whole fan, and we're still not seeing much. They prefer warmer slopes, like equatorial and west-facing slopes. And not all sites that have exposed bedrock, kind of like I showed in Tivit Crater there, that equator-facing slope, the north-facing slope, it did not have any RSLs, and other craters just don't have RSLs. They have exposed bedrock, they have steep slopes, but no RSL. So there must be something special that's happening in that subsurface, some special plumbing. So here's just an animation of Tivit Crater here. So here in green, you're actually seeing the RSL lengthen. This guy's lengthening right now. And then these guys will continue to lengthen. And then when we switch to the red squares over here, everything is just stopped lengthening. And then they'll actually fade when it gets to blue here. So what this is showing, this is just L sub S down here, and this is different Martian years as it goes. So now we're faded. Now the RSL is starting back up again up here. I'll just let that go a little, just so you can see the recurrence and how these things are actually incrementally lengthening. So this is, we think, is just water flowing downhill on Mars. These slopes are about 40 degrees at the steepest, and they come out to about 25 degrees when they stop. So now one of the big questions is, how do these RSLs compare to gullies? So if you remember, around 2000, gullies were found on Mars. People thought they showed that liquid water had flowed there in the last 5 million years or so. So these are the gullies. These are always on pole-facing slopes, while the RSL are on more equatorial-facing and more west-facing slopes. So these are RSLs just kind of highlighted in this red here. The gullies are actually much bigger. You can see the gullies in this picture. You definitely can't see the RSL. As we zoom in, you can see this is nice gully structure. We've got an alcove here, a channel, and then an apron down here, typical gullies. We're going to zoom in here where we actually have some RSL. So these are the RSL. You can see these little tributaries coming down, forming bigger flows, and then flowing all the way down here. So this is in the alcove of a gully. So, is it coincidence that we're seeing this? Probably. So the motivation for this talk. We were skeptical when we first heard this news, and that's what kind of got us going on this, and we've just kind of gone down this rabbit hole really, really far. Can water really be forming these RSLs? In case you hadn't heard, water's pretty unstable on the surface of Mars. There's really low water vapor pressures. When the surface temperatures are up at their highest, the relative humidity is basically zero. You'd just be pulling the water off, if it's not boiling it, because there's just no pressure there. And then we've also got low temperatures in the subsurface. Mars can get above the melting point of water, but it's very difficult to do that in the subsurface. So what's the formation mechanism and the recharge mechanism of these RSL? Do we have yearly recharge, or are we just depleting some larger reservoir? All right, so now I'm going to show you a map with all the candidate and confirmed RSL sites. But first, this is kind of my legend here. This is a Venn diagram. Each one of these circles represents one of the three characteristics of an RSL. If it only has one, it's going to be shown in blue. If it's got two of these, it's going to be shown in green. If it's got all three of them, it's a confirmed site, it's red. You should definitely believe this is an RSL site. All these other ones could go away. The white-filled ones, we've got like 1 or 2 images, and we don't see any of the recurrence or lengthening or fading. But I'm fairly confident it's an RSL, but you really can't believe any of these until they're actually confirmed. So here is this is molar topography showing from 60 degrees south latitude to 60 degrees north latitude up here. These are all the RSL sites. This is an albedo map. You can see the RSL sites seem to prefer darker areas on Mars. They don't like the dusty areas. So there again, we've got this one guy sitting out here. This is one of those white ones that just look like an RSL. It's probably going to go away if we get a repeat image because it's in this lighter area. It doesn't seem to follow. It's an outlier. But that just kind of shows you the confidence here to have. So now we actually have 110 sites of these. We used to call these very rare. We keep finding more and more. The HiRISE team is getting very good at figuring out where to look for these. We've got 34 confirmed. So looking at the molar topography, you don't see any dependence really on elevation. I mean, you don't see them on the volcanoes or Tharsis Plateau, but really other than that, you see them in very low areas in Valles Marineris. You see them in the northern lowlands. You see them in the southern highlands. You see them in Hellas. It's not like once the pressure gets above 6.1 millibars, that all of a sudden you have RSL. It's certainly not like that. Then we've got, these are the 3 regions I've broken it down into. So we've got Acidalia Planitia up here in the north, Valles Marineris right around the equator, and then the whole southern mid-latitude band. Well, just to go back, another reason, yeah. Yeah. Go ahead.
I just want to how many images do you need to make the confirmation, and if that can be by seeing the map on where you have multiple images?
Yeah, so the minimum amount of, So how many images do we need to actually confirm a site? Well, we need at least 2 to show the incremental lengthening, and then we need 1 to show it faded, and then we need another one to show that it came back. So I guess that would be 4 images we need at minimum. Yeah, go ahead. Yes.
How many of those are associated with gullies?
Depends what you exactly call a gully. If you go with the alcove, channel, apron, not very many of them. There's a lot of these drainages, more the equator facing. I don't know if you want to call it gullies. I mean, you see these great chutes coming down that looks like they're stuff flowed through them, but they're not really the official Malin and Edgett gullies. And most of these sites, again, the RSL are equator facing, where most of the gullies are pole facing in the mid-latitudes, somewhat. Yeah. And then we've got the ones in Valles Marineris, which don't really have many gullies, but lots of drainages. All right. So what I was going to say, one of the reasons why we don't have a band in the north is because many of these areas are actually dust covered. So if they weren't dusty, maybe we get RSLs at these elevations too, but maybe not. Okay, so what I'm going to do now is we're going to correlate the RSL activity with surface temperature. So we separate by region. We look at a series of these high-rise images. We're looking where the RSLs stop, when they start lengthening, when they stop lengthening, and then when they begin to fade. We have surface temperatures. We use TESS. We use MCS, Themis. And then we also do some modeling. That's what Tim Michaels does, kind of this model to figure out what the surface temperatures are. So now we're going to first start in the south, southern mid-latitude sites. So here we have 34 sites, 17 confirmed. So this is half of the confirmed sites are in the south. So just to kind of get my definitions, just to tell you what my definitions are. So this is what they look like when they're dark and lengthening. This is dark and static. So you can see the RSL itself has faded, but it is still darker than the surrounding material. I just lost the pointer. It's still darker than the surrounding material, and we haven't actually seen it retreating back. That's when we get into the start fading, when we actually start losing RSLs, where we did have a dark material, now it's just the same as the surrounding regolith around it. So here's the duration of the ones in the south. They last for about 100 days. They start right around perihelion. They stop kind of midsummer. And then we have, they're just static. They're just sitting there. They're lighter than they were before, but they haven't actually started fading all away. Then they start fading away here. So now if we look at surface temperatures, this is TESS. So again, TESS has great spectral resolution, not so good spatial resolution. We're talking 3 to 6 kilometers per pixel. We're looking at RSL that are like 100 meters long. So this just kind of gives us some idea of at least what's going on with the temperatures here. You can see very warm temperatures. This is 273, this blue horizontal line. This is also the time of day. That's how they're shaded. So TESS usually has about a 2 p.m. orbit, and you can see it varies. Here's the temperature. So they start lengthening around 295. The average while they're lengthening is 298. They're stopping here, and then when they start to phase, they're very cold. Now we look at, yep.
So the colors are modeled.
The colors are the actual. Each one of these is a data point from TESS, and that is the actual time that it made the measurements. And we're just fitting this. So that fit is not perfect. These are surface temperatures, yes. So if we really wanted to fit this data perfectly, we should take into account the variations with time of day, but then you have a model, and that model is probably wrong, depending on what the thermal inertia is doing at all these different sites. So, yeah. So here's the MCS data. Again, we fit a nice line to it. This is more 3 p.m., same poor resolution. But again, what we're seeing is very warm temperatures. We're seeing temperatures above 273 when the RSLs are actually active, and below 273 when they're not active. We do not think this is just a coincidence.
What do you mean by solar time?
Solar time, so
What is noon?
so noon would be when the sun is directly ahead.
Number-wise.
It would be 12.
12.
That's noon. Yeah, military time. Yeah, sorry. All right, so now we get to Themis. Themis has a lot better spatial resolution. One of the problems was with Themis is that in many of these areas, the Themis data is actually clipped or saturated in the PDS data. It's actually not saturated if you look at the raw data. So we're going back and reprocessing these. I haven't done this yet on the south ones. I've done it on the north. So anyways, these are kind of minimum values, but again, you can see these are above 273 for the most part when they're active. These are going just, we have no upper bound on these. That's because they're clipped or saturated. So if we just take the two fits that we have for TESS and MCS, you can see how symmetrical this is, where they start and they stop lengthening. We're always getting lengthening above 273. We think this is actually flowing water. It's actually liquid here, and then it freezes out, and then eventually fades away. So one of the ways to come up with a formation mechanism is really to figure out, is really to study what happens when there's an external force. And we got our external force in Mars year 28. This is right when Chryse was getting into orbit, a good mapping orbit. These were like the first pictures that came down, and of course, we got this planet encircling dust storm. So Chryse couldn't even really see the surface. This dust storm lasted for a considerable period of time, for really the southern summer. And so what would you expect this would do to the RSLs? Well, it actually made them bigger. This is just a coincidence. Well, this is Asimov crater. This is in the south mid-latitudes. This image was taken right after the dust storm, right after the dust cleared. And then we have another image that's taken 2 years later, almost the exact same L sub S, almost the same emission angle. So you can see how the RSL, which are right in here and over in here, how much longer they are, and also how many more there are. Look at this slope here. We've got all sorts of RSL, many tributaries and stuff, and then in the non-dust storm year, there's just not very many of those. If we keep looking, we can look at this crater. This is a central peak of a crater. This is right after the dust storm. You're getting all sorts of these features over here. And then when there's been no dust storm, there's just nothing coming there. There's no sources there. What we think is actually happening here, these are ridges. There's definitely bedrock beneath this, but it's covered with some regolith, which acts as an insulating blanket. And when we increase the temperature due to this dust storm, we actually get melting here. That tells us there's a big source down there that's just waiting to be melted. Here's another example. This is another central peak. We're actually seeing RSL on pole-facing slopes right after the dust storm. We don't see this in the non-dust storm years. I don't have a great image to compare it, unlike the other ones. So what we did is we did some surface temperature modeling. So Viking 1, a long time ago, before I was born, was taking measurements on the surface, and it weathered one of these dust storms. And what it actually found was that, just as our models predict, is that during the maximum time of day, where temperature should be the highest, the dust is not letting as much sunlight get down, so the maximum temperatures are lower. During the cold of the night, the temperatures are actually higher than that because of IR, downwelling IR radiation that's warming up the surface then. Here's what the subsurface temperatures are doing. So we're actually seeing a slightly warmer subsurface, but again, the maximum temperatures aren't getting very high. So again, this was actually a dust storm, the Viking image, that was a solstice storm, right around 270. Then we've got more of an equinox storm. This is actually what TESS saw in 2001, and it was able to see through this dust and actually map what was going on with the surface temperatures. And it saw a decrease, just like Viking did. And then it also saw an increase at night. So it saw a decrease in the maximum and an increase in the minimum temperature. So again, these are the subsurface temperatures. It's not really getting any warmer at that peak period of time, probably when these RSLs might be flowing. So now if we model what actually happened during this dust storm, this is a model of the Mars Year 28 dust storm. Again, this is a different storm. This is a solstice storm. It looks like the maximum temperature is actually staying about the same and the minimum temperature is raising. This takes the subsurface temperatures and raises them, and we think this is what's actually causing this, which is causing why we have so much more melting after this dust storm. So just kind of a diagram as to what's going on here. We have this big dust pall, this big dust cloud just sitting over Mars. And because this is a solstice storm in the south, you're actually charging is a bad word. You're actually heating up this dust. It's absorbing more solar radiation. It's getting warmer, and it has a longer period to get warmer because you have more sunlight as opposed to an equinox storm. And so it's getting warmer. It's giving you more downwelling IR, which is heating the surface even during the daytime and making up for the blanking out of the solar radiation. And then during the nighttime, you're keeping heat in and also putting heat into the surface. And so in a net effect, you're actually warming the subsurface. So this tells us these RSLs are very sensitive to temperature. And we consider these ones in the south to be temperature limited, meaning if it was a little bit warmer, we get a lot more melting. So here's our formation mechanism. We have discharge from the bedrock. We think this is actually ice melting in the bedrock. Then this ice melts, it flows into the regolith. It's about 5 centimeters thick. It's probably fresh water because the temperatures are so high here. It's flowing on an ice-rich aquitard. This ice-rich aquitard is formed from previous flows that just never fully sublimated away. Remember, we're seeing these every year. So it can't sublimate this whole thing. It's just kind of self-perching. The water's freezing down there. And then on top, which is actually making it dark, is we have these 1 to 2 centimeter thin films. These thin films are very important. They allow us to decrease the evaporation sublimation rate. So what's happening here, this is a diagram showing that if ice or even liquid water is at the surface, it would evaporate pretty quickly. Now if it was buried 1 to 2 centimeters down, or 10 to 20 millimeters, you can really reduce that significantly, almost an order of magnitude, the evaporation rate. This also allows you to have subsurface liquid water when the surface pressure is below 6.1 millibars. You're actually getting somewhat of a pressure gradient flowing through there. You've got tortuosity in the pores. That water vapor just can't immediately escape. You're actually building this up. We've actually modeled this. These thin films are also darkening the surface. as I said, and then we're also getting an increase in the thermal conductivity. This was actually modeled, a similar region was modeled by Peque in 2009. This was salt, just salt precipitating on the regolith. And he was just showing that with just a little bit of salt in the regolith, you can really drastically increase your thermal conductivity. Well, adsorbed water, these thin films are going to look very similar. And they'll be at about 1 to 2 volume%. So they're going to drastically increase this thermal conductivity. This gives you more heat into the subsurface. Plus you're darker, it's going to absorb more. So as these are flowing, you're getting evaporation and sublimation losses. We believe in the south these are much less than the discharge rate. And the flow is really just restricted by the permeability of the regolith and the subsurface temperature. So it's just how long you have to flow, how long it's liquid, because it's going to freeze every day. So when it's static and it's fading, we never get, the ice never melts, we never have liquid, and it just sits there and slowly sublimates away. That's why it takes over 100 sols for it to happen before it starts fading. And then when it's completely faded, your entire, all your ice is gone, and you keep this aquitard just because it's so deep and it just can't fully sublimate away before the next year starts. So we've modeled this using a Mars flow, which is it can model all 3 phases of water, gases, and then we've also used hydrological codes. The permeability of the observations matches a clean sand, and we get a water volume for each RSL of about 2 to 10 cubic meters of water per meter of head wall. So I'll show you how that compares to possible recharge rates after I explain this. So this is Raga Crater. This is another RSL site. So we're looking for a volatile source. What's actually sourcing these? What's causing this recharge? So here we have a bunch of pedestal craters shown in red. So these are craters that occurred probably when this unit that's shown in black used to be much more massive. Would have extended further south here and further to the west here and covered this. These impact craters occurred. They threw out ejecta. It covered it. It blanketed this volatile rich area. This ice was not able to sublimate away as it was everywhere else around it, so these are now high spots. This is currently sublimating back. This is the ejecta blanket of Raga Crater in purple, and then kind of in this pinkish color is really where the rays go. We're going to zoom in on that. This is where the RSLs are actually occurring on the equator-facing slopes. And then if we really zoom in on this ray here, you can actually see all this dissected terrain around it, which is showing this is a very volatile rich, probably ice. This is the latitude-dependent mantle. And then you've got more material over this, which has actually been protecting these volatiles. All these albedo changes are really just due to dust devils. So we think this is actually the source, but the southern mid-latitudes and even the north are very volatile rich. There's a lot of ice just sitting there, and somehow it's flowing probably in the subsurface and being captured over here, possibly being cold trapped by the bedrock, and then melted when the temperatures change and it starts getting a lot warmer. That was our idea. The problem is that the subsurface vapor diffusion really only gets us this amount of water, so 0.2 to 2 cubic meters per meter. This is not enough. We were estimating the recharge to be 2 to 10 cubic meters per meter. So, you know, this 2 value is close. This is a very optimistic number, very warm subsurface, probably not really that realistic. So we really concluded that maybe this flow is more like raindrops on a window, where it's not actually a saturated flow, where you get these raindrops and they're just kind of waiting to flow. They're on the verge of flowing, and if you get one that makes a nice path and kind of wets the surface, then another one can follow that path. So you might get melting up at the top, and these different drops or slugs are following that. We need to do more modeling on this, but these recharge mechanisms are very difficult, as you'll see through here.
Can I ask a question about
Yeah.
this? Can you expand on what you mean by cubic meters per meter?
Cubic meters, yeah. So it's cubic, so it's the volume, and then the per meter is the meter of head wall. So as we go around on I don't have a great picture. Maybe I do it down here. So this is actually one in the south. So, so the cubic, so we have a volume. So you understand? Yeah, we have a volume going down, and then the per meter of head wall. I lost my pointer. Is it's just along the head wall for each meter along that head wall. I hope that makes sense.
Like a flux.
It's yeah, it's just a flux, and yeah, it's just a way to parameterize this. And then, because all these RSL sites are different, they have a different different amount of RSLs per site. And, yeah. Okay, so now we're going to switch to the ones in the north, Acidalia Planitia. We're going to zoom in here. So now, just to kind of show the observation bias, I've put in these boxes that are not filled, and so you can see that we have good high-rise images, of these. You can, if you look close, you can actually see craters in there. These are these steep slopes, outcropping bedrock, no RSL, and then, right nearby, we actually are seeing RSL. So we have 3 confirmed sites here and 19 total sites. These have really been growing. They've really found a lot more in just this last Mars year here. Again, these are dark areas. Also, these don't go as far poleward. The ones in the south go up to 52 degrees south. These only go up to about 42 degrees north, probably just due to the temperatures. So here's the lengthening. As you can see, the duration is significantly different than before. We're seeing a significant amount of length. We're seeing 334 days of lengthening. It's actually lengthening possibly in the wintertime, right around equinox, possibly even before equinox. Stopping all the way over here and then a short static phase and then fading away. Another thing that's different is before we have all these very small tributaries that are being shown here coming straight out of the bedrock. The ones in the north are a lot more diffuse. I mean, they completely saturate the ground around them. I think it's coming out over here. This is kind of a zoom in of this. I think there's a fracture here, maybe a fault that it's coming out of, and it's completely saturating the ground, but it could be coming up here. Many of these ones in the north, it's really hard to tell exactly where it's bubbling out, onto the surface, because they just completely saturate the area. Where in the south, we actually have individual tributaries coming out. This is another hard plot. We've got some biases in the beginning and the end of this. This is the maximum lengthening rate that we're seeing with these. So we're seeing a pretty constant lengthening rate in here of about 0.2 meters per sol. That's how fast they're moving. And the reason it's a maximum is because many of these ones in the north are actually static almost the whole time. So I just picked the one that's moving the most, and that's why this is a maximum value. So what's happening in the beginning here is we have a high-rise image right at this L sub s, and then we have a second high-rise image here. This first high-rise image had no RSL. The second high-rise image had a huge RSL, like over 100 meters. So we just divide how many sols took place in there, we get this nice average value. But in reality, this is probably actually much bigger because it didn't start flowing right after we took the picture, and it probably slowed to a much slower rate, before we took the second picture. So this could actually be, a much bigger surge. So we get this big surging of these RSL, and then they slow to this more to a slower rate. What's going on here, why they're not stopping, is kind of the same thing happening. We take a picture, we have an RSL here, it lengthens, but we don't take another picture of it till over here. So then we get this rate. It probably actually stops somewhere in the stop lengthening time frame, and so this should actually probably be moved up a little bit. So now just to kind of show you what that looks like when we're looking at these actual images. This is another crater, 2.3 kilometers in diameter. In the north, we see RSL all along the west-facing slope here. This doesn't have any RSL in it. And then the next image, you can see this giant RSL peeking out. And then we've also got RSLs all throughout here. So just to show this RSL is over 100 meters long. It just popped out. And then these aren't orthorectified, unfortunately. You can see this RSL will continue to lengthen, where this is, it may be barely lengthening. And some of these too, they lengthen a little bit, but this one really lengthens a lot. You can see it's just coming over this kind of this rocky outcrop, There it is again. It's flowing downhill. It's getting into these rocks now. Then it's going to break apart into two different flows and continue flowing down. But it's flowing at that very, like that 0.2 meters per sol rate. So now if we look at the temperatures, so instead of showing all the individual data again, I'm just showing the fits. We've got tests again at 2 p.m., which is, of course, the warmest. The maximum surface temperature happens around noon. We've got MCS about 3 p.m., and then we've got Themis. This has been corrected for the saturation effects much later at 4 p.m., much colder. We actually don't have any Themis data beyond this point. The Themis team has just, I guess, stopped taking pictures because it's just so cold in these regions. So now if we can compare this actually to these lengthening rates, you can actually see where we're getting this big surge, this maximum rate. We're actually seeing, very cold temperatures occurring then. And then, we see temperatures rising, we see stop lengthening, and we've got, still pretty warm temperatures. And then we don't really get back to where we started, until we start fading. Also, this cyan line is at the eutectic point of sodium chloride, which is 252.1 K. Just to kind of show you some, just to compare. So now if we compare Acidalia Planitia to the ones in the south, this is Elsevesse again. The ones in the south were much warmer, much shorter duration compared to these. We're actually seeing this double hump again. This is actually due to aphelion. So Mars is getting further away from the sun, so the temperatures are naturally cooling down. That kind of gives it this double hump. So what's causing these? What's the formation mechanism behind this? We actually think these are forming from fractures. We're actually getting discharge from a fracture and also our recharge there. We actually think this is fresh water that's actually discharging. But then it's immediately dissolving salt that's been trapped in the regolith. Again, we're around 5 centimeters. This could go up to 10 centimeters. 50 centimeters would be pretty deep because it's really tough to melt something that's 50 centimeters thick every day. This is probably a eutectic brine. Below it, we've got an aquitard. It could be actually a salt-rich, kind of like a caliche-like aquitard, where it's salt that's being precipitated out, and it's not able to dissolve any more water because we're already at this eutectic mixture. So a eutectic mixture can't dissolve any more salt. And then we've probably got another 1 to 2 centimeters of these thin films, just to protect it from the harsh environment up above at the surface. So why are we getting this big surge, this high lengthening rate? So at first, the evaporation and sublimation losses are much smaller than the discharge rate. So we've got a high discharge rate here. We've got a very small RSL. The surface area of the RSL is really proportional to how much evaporation losses you have. So as the RSL grows, the losses get bigger. Then it reaches this small lengthening rate where it's just smaller. The losses are just smaller than the input rate, the discharge rate. And then eventually, when they become static, we actually have evaporation sublimation losses equaling the discharge rate. So here we have equilibrium flow. So everything that's coming into the pores here is being replaced by we're losing water via the evaporation, and it's being replaced by the recharge or the discharge. We also think that in this mechanism, you can actually get salt flowing back uphill. You just got this kind of standing body of water, it's very slow moving, and the salt's going to diffuse. So when it's faded, the salt doesn't sublimate away. It's just left there in the regolith, waiting for next year's flow. So what's coming out of these fractures must not be like a eutectic brine mixture. Otherwise, we just start clogging the pores. So that's why we're calling this fresh, and maybe it's coming out of an ice dam. Maybe once that ice dam breaks, we can start getting flow, and that's what's happening when it starts lengthening and really surging. So we've modeled these two for a water budget and figuring out what the recharge rate might be. We've got a nice permeability of clean sand again. The RSL water volume is like 10 times bigger, 30 to 100 cubic meters of water per meter of head wall. And so it's really tough to get this amount of water in like half a Mars year. This is why we've got this fracture flow, and we think it's coming up from an aquifer under Acidalia Planitia. We realize this is pretty kind of a crazy idea, but we can't come up with anything better yet. So what would an aquifer look like here? So we just connect the ones that have been incrementally lengthening and the confirmed sites. We've got a pretty good aquifer down here. One of the problems is how do we actually get this water up to the surface? So maybe it came, maybe it was recharged, from the highlands, and it's a confined aquifer, and then these fractures are busting through this confining layer. Maybe it's like Pingo Formation, where you've got ice forming, it's freezing in, and the ice is expanding and pressurizing your aquifer. It's very difficult no matter what, but the observations are there. We just have to come up with a good idea to figure out what's going on. So now we're going to switch gears, go to Valles Marineris.
So before you do that, can I ask?
Yep, go ahead. I'll repeat it.
So this, especially these very, the temperature dependence of these, the idea of fractures forming, how do you explain the temperature dependence of the fact that these things turn on and turn off as a function of temperature?
Yeah, so the question is what's causing the temperature dependence of the?
Why would the fractures form? What would?
So the fractures
Why would temperature dependence cause fractures?
Yeah. So okay. So the fractures are there from the impact crater. So there's probably fractures that are going very deep just from the impact crater. Why? So we think there's actually an ice dam on that fracture, and once that ice dam melts, the water can come out of this fracture.
Okay, but they're turning on it way below.
They're turning on way below. So once the liquid water comes out, it dissolves salt and is able to flow at this eutectic temperature. But yeah. There's.
Why can't the reservoirs be actually salty water reservoirs?
So if the reservoirs were salty reservoirs, you've got a problem with the salt. How do you get rid of the salt? So if you did have a eutectic concentration of salt down there, you get this salt that shoots up this fracture, it flows down, and then all that water sublimates away or evaporates away. You're left with all this salt still in the regolith. Then the next year, that eutectic brine comes back up again, flows again, and it hits all that salt, and then it all goes away, and you're just building up salt. You're just continuously building up salt, and that's going to.
Salt in the spectrum at all?
No, there isn't, and we think that's because it's occurring in the subsurface. At the surface, I think it's just these thin films, and you should get some salt wicking up there, but maybe it's just not more than the typical amount that we're seeing on Mars. I don't have all the answers yet, but these are really tough. Oof. Okay, so here's Valles Marineris. In case you don't know, Valles Marineris is really big. If it was on Earth, it would stretch from like LA, Los Angeles to New York City. It's very deep. It's about 7 kilometers deep. We're seeing a lot of RSLs in here. 56 sites. This is more than half of the sites are actually in Valles Marineris. 14 confirmed. I'm going to zoom in here. This is Coprates Chasm. This is a big canyon. I've again shown the blank rectangles just to kind of show the biases. What you see is that there's absolutely no high-rise images really in here that we don't see RSL. So anytime we see a high-rise image, we are actually seeing RSL along this ridge here, which is really hard to explain if you want to do an aquifer. It's really got to be pressurized. We're talking like 7 kilometers of head that it has to jump. Yeah. This is why we haven't worked on these as much. It's really hard. And then we've also got we've got craters on the floor that are showing RSL as well. These are huge. These are 10 times bigger, 2 to 10 times bigger. It's actually hard to show this. There's RSL that are occurring all the way up this slope, very tiny. They get bigger and bigger and bigger as they flow down. You can see them down here. Another one, another one, another one, another one. So we've got a lot bigger source regions here. There's a lot more bedrock for them to be flowing out of. We've got just longer, really steep slopes, and we actually have a longer duration, as you'll see. So here's one of these craters that's on the floor of Valles Marineris. This is 2.5 kilometers in diameter, and the RSL are found on the warmest slopes. So right now, the image is showing southern summer, so we're actually going to see RSL over here. Now it flips to northern summer, we see RSL on the north-facing slopes. And as it goes, now it's going to flip back over. We're going to see RSL start occurring up in the south-facing slopes again. So this is kind of like a sundial. It's just following the slopes that get the most sunlight are where we actually have the RSL. Just due to time, I'm just going to skip over this real quick because I'll talk about it a little bit later. So these things also lengthen slightly differently. Here we have two different images, taking a few L sub s apart. And what you're actually seeing, you're seeing a lot of lengthening going on here, but you're also seeing fading at the same time you're seeing lengthening. So this is the earlier image. And if you look right in here, this RSL is going to go away. And it's replaced by another one. So we don't think these are equilibrium flows. So you can see this going on many places. Again, right there. So these aren't equilibrium flows. We think these are more the surge flows. We get this drop of water going down and causing these RSL. Again, these are much bigger. Just looking at the temperature dependence, this is just of that site, why we don't have a whole lot of data. We've got test data here. We're breaking over 273 at times. Again, we've got just, the test data pixel is as big as the crater. So then we've got MCS, which is, similar problem, but we're not getting over 273 very often. We've got Themis data. This is the CLIP data, so it should actually be, it's going to actually turn out to be warmer than this, but it's still not above 273 a lot of the time. So therefore, we think this is brine. This is just showing when it's lengthening. Getting a lot of curves on this map. This is just a temperature going on, surface temperature that we modeled. You can't really believe the surface temperatures absolutely. This is more for kind of relative comparison. It really depends on what the thermal properties are doing, depending on exactly the absolute values of these. Just to break this down, we're actually seeing our lengthening on the south-facing slopes, starting over here. Then we get this brief period of no flow. These kind of wiry areas are very, very small amount of lengthening. Basically, I never saw them before until we got the orthorectified data, and then by just flipping back and forth, you could actually see just a little bit of movement. The white-filled ones show very minor movement, and the completely filled-in ones show major movement. So what's happening here is you're actually seeing flow pretty much when the temperatures are at their maximum, except for we kind of have these kind of holes in our data. There's possibility that this could have been disrupted by dust. Right now we're at L sub s 210, so we're actually going to start filling in this hole yet again, and we'll see if this is a real hole, if this was just some sort of a local dust storm that occurred there. So these are the ones in the north. They're flowing for more than half a Martian year, almost 3/4 of a Martian year. And they're flowing significantly. We still don't really know if this gap, if we have continuous flow, we're into our next Martian year, but they actually didn't take a high-rise image in this big blank spot here. They took it afterwards, so I don't really know if it was continuing on from this one at 90 or not. But it sure looks like it is. It's hitting a minimum value right around that point too, which is strange because over here we're not actually getting flow. But the surface temperature should be warmer. So, maybe there's a source issue going on here where these RSL actually have to recharge sometime. They have to sit there and wait to fill back up this near surface reservoir, or else maybe the head is just being pulled away from these north-facing ones to the south, because this is when the south is very active. So maybe there's only so much head in this aquifer, and it can only put out enough water to be throwing RSLs on the north-facing and the south-facing slopes. It's a question we hope to answer sometime. Here we go with the duration. We've got almost 500 sols in the north-facing, and then we've got 300 on the south-facing slopes. What's the volatile source? There's been proposed lakes right along here where we're seeing most of our RSL. this lake was proposed by Harrison and Chapman to form the outflow channels. They mapped a bunch of these benches that actually look like lakeshore deposits, was their interpretation. And this lake might have left behind a deeper groundwater table that maybe is being accessed by these RSL. Another more recent paper just came out this year saying that instead of these benches being shorelines, they're actually trim lines where the glacier just cut through these spurs from Valles Marineris. These glaciers were, again, about 3.5 billion years old. And they believe that these glaciers are still there. They're still on the floor. They're very deep. They're like 100 meters below the surface floor. So, there we have a source of volatiles, but, how do you recharge it so quickly? It's very difficult. So now just kind of to discuss all these. This is the duration, depending on region. So we've got our ones in Acidalia occurring, very long duration. We've got our ones in Valles Marineris south facing, north facing, and then our southern mid-latitudes, which are very short duration. So what this means is that water is flowing somewhere on Mars every single day. So right now, we're at LCS 210. Water is flowing in Valles Marineris on the south-facing slopes. It's just stopping in the north in Acidalia, and it's just stopping on the north-facing slopes in Valles Marineris. Just to compare these, the south ones are warm, the short duration, probably not salty. They could be salty, but they also might be fresh. In Valles Marineris, we've got the longest ones. They're likely briny. In Acidalia, they're cold. They last about a half a Martian year. They're very briny, but we may have a freshwater source. So since this is SETI, I thought I'd talk about some habitability. If we actually, could an RSL actually be a habitable environment? We think they're very thin. Radiation is going to be a significant problem in all of these. The most habitable environment is probably in the south here. If you had a very radiation-tolerant bug, it could probably live for about 100 sols before it had to hibernate and make it through and survive all this radiation. These other ones are going to see low temperatures and salt, so very low water activity, which is going to be tough for life. So, what about the source? I think this is the most probable, where we've got an aquifer. This is a nice habitable environment. It's deep, it's away from radiation. It may not be salty. Even if it is salty, maybe you could still have a habitable environment there. One of the best features here is that this water is being brought up for you. All you got to do is go to the RSL, climb up that steep slope and scoop some of this out. Hopefully you could see a biosignature. Maybe if you get lucky, even a bug that's come up with the water. Really in conclusion, our observations strongly suggest that RSL are water slowly percolating through the near subsurface of Mars. RSL at different regions appear to have different recharge mechanisms and different salt contents. And RSL's recharge is really poorly understood. And with that, I'll go ahead and stop and take some questions.
I know there are going to be a couple of questions, so I'll just get mine in first. So do we have any radar coverage of particularly the Acidalia Planitia area where you might be able to look at is there any evidence of radar?
So we don't actually near Acidalia, where we're not actually penetrating Acidalia. However, in Valles Marineris, Isaac Smith actually has an AGU talk on this. We're actually seeing a deep reflector. It doesn't really correspond with where we're seeing the RSL. We're putting in high-rise suggestions to try to get more high-rise data there. It's kind of more in the dustier locations, and it could just be a basaltic flow. It doesn't have to be an ice table or a water table or something like that. But there might be something more in Valles Marineris. There's certainly nothing in the south. There's just too much clutter there.
Okay.
So can you go back to your slide about the radiation?
Yes.
I guess it's the habitability.
Yes. You may know more about this
When
than
you
me.
say radiation, are you referring to UV or what do you?
Well, not UV because these are buried. Just cosmic rays, just the radiations that's going to penetrate, at least 10 centimeters.
But the radiation penetrates very well down to a meter, so
Exactly, which is why this is not going to be a good location for bugs to be living.
Well, actually, I disagree with that because it's an issue of how fast can they grow. I mean, if they aren't growing, then yes, this is not a good place to be sitting for a very long period of time. But if they're growing, then they just have to outpace the pace that they're being killed by radiation, which isn't very fast.
Right. So when they're dormant, as long as they're able to maintain so there's different amounts of dormancy, right? So they could maintain that radiation damage. But that's when it's going to be very cold. So these ones in the south, they're only active for 100 sols, and then they have to, wither the rest of the over 500.
Right, but that's only a year, and
yeah.
the radiation damage in a year is not terribly significant. So I suggest you look at that. But another question I had, which is about the, you say there's no evidence from spectral measurements of salt or water. What are those spectral measurements?
They're from Chryse.
So it's Chryse? It's
Chryse data, yeah. So there's a paper written all up on this. Really, they see some more, basically they get a detection like hematite around, more ferric materials there. And so, maybe that's just because it's darker and the light is penetrating in deeper that they're getting more hematite, but
They may not be sensitive to the particular salt that you're interested in.
Yeah, that's right, yeah. Chlorides are very spectrally neutral.
Is curiosity near any?
No, they're not. If we'd gone to Hale, we might have been near one. Yeah.
Hi, thank you. It's been a long time since the Noachian era. And if we still have like free-flowing water on Mars, it's had a long time to sublimate, right, and go away. So I'm not sold on the idea that these are caused by H2O as opposed to some other mechanism. But
neither were we when we started.
Okay, I'm still not sold.
Yeah.
But so my question is to resolve the question of the actual chemical makeup of the thing that's creating these RSLs. It would seem to me that the proper thing to do would put a rover somewhere near one. So given that it's in places like craters and the Valles Marineris and other things like that, is there a good location, maybe near Viking 1, where we could put a rover and go like scoop this up and say, well, is there water there, or is it dry ice or whatever?
Yeah, that would be great. So this was one of my backup slides if I was running late. This type of a mission was thought about. Dave Page presented at the Mars Concept in 2012. He came up with an orbiter would be best. So we have planetary protection issues to get into these craters now. These are special areas because they might be flowing water, there might be bacteria there. We could bring a bug that could actually colonize these areas. They're very rugged, Right. So yeah. But it's going to be tough to get up that 40-degree slope, 25-degree slope. Yeah, for sure. But it could be done. So Dave Page's argument was that let's send an orbiter there first, make sure this is water, make sure this is worth going to. These are the kind of instruments that you might need to actually figure that out, to figure out, really confirm that these are water, better local time coverage, repeat coverage, more than once a day, map actually the water vapor sublimating or evaporating out, and figure out what the temperatures actually are of these, by actually imaging their temperature instead of these giant pixels that we're doing now. So yes, it would be great to go there. That would solve all our problems, but unfortunately, we can't.
What's the lowest angle slope there?
About 25 degrees, maybe 20 degrees. Yeah, on those big fans that are coming out.
Oh, yes, more than observation. Wow, water every day, so exciting for astrobiologists, habitability. It's a plenty of time. I mean, there are hundreds, tens to hundreds of days there.
Yeah.
And it's not a matter of whether or not the life arose. I mean, it might take billions of years. But if bugs are there dormant, they could be as quick as no, say minutes, but hours, could be fast cycles of hours and few days where you get the maximum habitability conditions. So that could be a great place where
Yeah,
to look at that
yeah,
for
and
life.
it's looking like we're getting melting for a few hours, for
That-
sure. And it really depends on what the salt content is and everything, up to 8 hours a day.
That
Yeah,
could be
possibly
enough.
liquid.
I mean, that could
Yeah.
be pretty enough. There are examples of that. The other thing was about the salt.
Yeah.
Do you have, is a detection problem about the fact that TEMIS doesn't see salt, like very, very ppm? I mean, there is a detection limit where it's
Yeah, so
just
where
in your-
Chryse sees the salt, so a lot of the chloride salts and probably the perchlorate salts too are pretty much invisible to spectral analysis. You can see sulfates and things like that, but they don't have significant freezing point depressions. So it is very difficult to find these salts, using remote sensing techniques.
Okay, I know there are some more questions, so please feel free to come up and speak to David after this. David, we have a special SETI Talks mug there for you. It's got a couple of robots. Maybe they're Martians talking about how the RSL works. They probably don't have a clue. Right?
Yeah.
So please join in thanking David for his great talk.
Thank you.